Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 27 of differential geometry. Last time हमने diffeomorphic surfaces के बारे में पढ़ा था और ये हमने देखा था this is very important class of maps जिसमें हम differential geometry के point of view से कहते हैं कि when two surfaces are equal from the differential geometry point of view. उसके बाद हमने mapping of differential forms पढ़ी थी कि एक सरफेस से दूसरी सरफेस पे अगर एक मैपिंग गिवन है तो एक सरफेस की डिफरेंशियल फॉर्म्स को आप कैसे मैप कर सकते हैं टू द डिफरेंशियल फॉर्म्स ऑफ द अदर सरफेस। आज हम इससे स्टेप फॉरवर्ड लेंगे और ये देखेंगे कि कैसे एक कर्व को यूज करते हुए इंटीग्रेशन कर सकते हैं ऑन एनी सरफेस। सो बेसिकली वी विल बी इंट्रोड्यूसिंग लाइन इंटेग्रल्स ऑन सरफेसेस। उसके बाद हम देखेंगे हाउ टू इंटीग्रेट टू फॉर्म्स और उसके बाद हम इंटीग्रल ओवर ए बाउंड्री को देखेंगे। सो बेसिकली दिस इज पार्ट ऑफ आवर प्लान जो कि हम शुरू के लेक्चर्स में भी डिस्कस किया था। उसके बाद भी मैंने आपको बताया था कि व्हाट इज द अल्टीमेट एम। सो लेट्स से वी हैव ए कर्व इन R2, प्लेन के अंदर एक कर्व है। हमने कैलकुलस में ये चीज़ें पढ़ी हुई हैं, हाउ टू इंटीग्रेट दिस कर्व एंड हाउ टू डिफरेंशिएट दिस कर्व। सो लेकिन अगर यही कर्व किसी आर्बिट्रेरी सरफेस के ऊपर है देन द क्वेश्चन इज हाउ टू इंटीग्रेट दिस कर्व विच इज लाइंग ऑन एन वेरी आर्बिट्रेरी सरफेस। सो आज का जो लेक्चर है ये इसी सिलसिले में पहला लेक्चर है। इसमें हम देखेंगे कि अगर कोई भी कर्व सरफेस के ऊपर है तो हम कैसे लाइन इंटीग्रल कैलकुलेट कर सकते हैं ऑन दैट कर्व। सो स्टार्ट लेते हैं हम। लेट अल्फा बी ए कर्व और उसका एक क्लोज्ड सेगमेंट। सो क्लोज्ड सेगमेंट मींस उसके जो एंड पॉइंट्स है वो इंक्लूडेड है ऑन ए सरफेस। So M is some surface and alpha is basically a map from some closed interval AB to the surface M. सबसे पहले इंटीग्रेशन के लिए हमें वन फॉर्म्स की ज़रूरत है। ये बिल्कुल ऐसे ही है रफली स्पीकिंग जब आप इंटीग्रेट कर रहे होते हैं इन R2 तो इंटीग्रेशन में आपके पास कुछ इस किस्म के एक्सप्रेशंस आते हैं f of x dx। अब ये जो dx है इट इज़ ए वन फॉर्म। सो वी नीड वन फॉर्म्स ऑन दिस सरफेस M और एज ए मैटर ऑफ फैक्ट we need one forms on this curve to integrate along this curve. So we start with one form और phi हम कोई सी भी one form ले रहे हैं on this surface M, उसको हम pull back कर रहे हैं to the one form on AB. So basically इसको हम pull back करेंगे phi को। So basically we will be seeing this. So what is this expression? What is the pullback of phi on this closed interval? So ये चीज़ हमने बार बार देखी हुई है that every one form can be written as, so in R3 every one form can be written as f1 dx1 plus f2 dx2 plus f3 dx3. But on R1 or some closed interval contained in R1, so this AB is a closed interval contained in R1, then every one form can be written as, so on R1 every one form can be written as some function f of t and dt where t is the parameter on this interval. So we need to find this function f of t, because dt is just the differential of the coordinate function t. So how to find this t? और ये हमने ये देखा था that this f of t is image under this one form of this natural frame field. So this is the pullback of the one form, and this is applied on this natural vector field. So this is equal to, by definition, phi of the tangent map alpha lower star of u1 of t. So if t is any point on this interval, then u1 of t is a vector, unit vector from this point in the direction of positive real side. So this is u1 of t. अगर t वेरी करेगा तो definitely ये vector वेरी करेगा. Now what is alpha lower star of this tangent vector? So alpha lower star, or the map which will take tangent vectors to the tangent vectors, will be in fact taking the image under alpha of this vector. So basically this will be the velocity vector at point alpha of t. So this is in fact alpha prime of t, and so f of t is nothing but phi of alpha prime of t. So what we have done so far, given any one form on the surface, we can pull back to this closed interval AB, and it has the following form: f of t dt, where f of t is equal to phi of alpha prime of t. So basically every one form can be written, can be pulled back onto this closed interval and can be written as phi of alpha prime of t dt. Now we are ready to go to the next step. Let phi be a one form on M, and let alpha from AB to M is a curved segment. So curved segment means it is image of some closed interval of R1, और इसमें जो end points हैं वो भी included हैं. So this is a curve segment. So basically अगर मैं तमाम interval consider कर लूँ, then this curve will be something like this, but I am just considering the segment from this point to this point, and this point is alpha of A and this point is alpha of B. Now the integral of phi over alpha is equal to, now this is the definition which we have been waiting from long. So this is the definition how to integrate phi on this curve alpha. And the definition is very simple, that you pull back this one form, and we know how to pull back a one form onto this closed interval, and take the limits of integration a b. और ये हमने अभी देखा है that the pull back of one form onto this closed interval is nothing but phi of alpha prime of t. So basically we have this definition, which is very important definition, and it has very important applications and consequences in mathematics and in engineering and in general science. So let me write it again, that if you want to integrate a one form along a curve alpha which is lying on a surface, then this is nothing but the pullback of this one form onto this closed interval. So उस one form को pull back करें using this function alpha, or the pullback is alpha upper star of phi, and the limits of integration are AB. And we have just seen that every one form on this closed interval, which is a closed subinterval of R1, can be written as phi of alpha prime of t, and the limits of integration will be a to b dt. So that's how we integrate any one form on the surface. So basically, why one forms? So once again, let me take you to calculus, where we integrate things like f of x dx. Now if you closely observe, what is f of x dx? It is a one form. So we are integrating one forms on R2. So all we needed was how to integrate a one form on a curve inside a surface. So that was the requirement, and now we know how to integrate a one form on a curve which is lying on a surface. Now let's apply this definition. So let V be a vector field on a surface M. So for example, surface is a sphere, and vector field means each and every point of the surface has a vector associated to it. So for example, consider Earth and consider the gravitational field around Earth, or consider the magnetic field around Earth. So gravitational field means at each and every point around Earth there is a vector. So at each and every point around Earth there is a vector associated to it, and if you go far from Earth, then this vector becomes smaller and smaller, but close to the Earth these vectors are bigger, because the magnitude of the force close to Earth is higher than for the points which are further apart from Earth. So there could be many examples of the force fields. So just take one vector field on the surface M. We assume that V is a force field. So for our next discussion, we assume that it is a force field, and assume that a particle moves on a curve alpha. So on this surface there is a curve alpha, and which means there is a map from some open interval I to the surface M, and this image is called the curve on the surface, and there is a particle which moves along this curve. So it could be any particle. So for example, planet Earth पे कोई particle move कर रहा है, कोई car move कर रही है, कोई object move कर रहा है. Similarly, कोई सी भी surface है in general, उसके ऊपर एक particle move कर रहा है, but in the presence of a force field. So there is a force vector at each and every point on the surface. And we want to know how much work is done by the force on the particle as it moves between the points alpha of A and alpha of B. So let's say A and B are 2 points inside this open interval I, and let's say this is alpha of A and this is alpha of B, and we want to calculate how much work is done if the particle moves from this point alpha of A to this point alpha of B. So इस path के along on the surface particle move कर रहा है और हम work done calculate करना चाह रहे हैं by this force. Now to calculate work done, we need to calculate the component of the force tangent to alpha. So this is the component of the force which will be responsible for any work done. So और कैसे calculate करेंगे? So V is the force field, and at any point, so let's say this is the curve alpha, किसी भी point पे I can calculate alpha prime, and I can normalize it, means I can divide it by its norm and I will get a unit vector. Okay, now what is V of alpha dot alpha prime over alpha prime norm? This is basically, so let's say this is V of alpha of t. So basically this is alpha of t, some particular point on the curve, and V of alpha of t. This is the value, or this is the tangent vector associated to the point alpha of t, and you can also say that this is the vector associated to this point, and this is the force vector. ये वो force है जो कि आप exert कर रहे हैं particle पे at this point alpha of t. So इस point alpha of t पे इतनी force apply हो रही है which is V of alpha of t. अगर मैं point change कर दूंगा definitely ये vector change हो जाएगा, and how I will calculate, so for example at this point the force vector could be something like this, or let's say this is the point alpha of t naught, then this force vector will be V of alpha of t naught. So इस point पे जितनी force apply हो रही है by this force vector field is V of alpha of t naught. So अगर मुझे calculate करना है the component of this force vector at this point alpha of t in the direction of the tangent, तो मैं dot product ले लूँगा of this vector with the unit vector in the direction of the tangent vector. So ये चीज़ हमने पहले भी देखी थी जब हम डिस्कस कर रहे थे डॉट प्रोडक्ट, कि अगर मुझे किसी भी वेक्टर का कंपोनेंट फाइंड आउट करना है, लेट्स से दिस इज वेक्टर v, उसका कंपोनेंट फाइंड आउट करना है इन द डायरेक्शन ऑफ सम वेक्टर w, तो बेसिकली मैं डॉट प्रोडक्ट लूँगा v का विद द यूनिट वेक्टर इन द डायरेक्शन ऑफ w. And so what is the dot product? So this is equal to norm of v, norm of w over norm of w, norm of w over norm of w into the cosine of the angle between them. Now this can be written as norm of v, norm of w over norm of w, cosine theta, and these two will cancel out and I will get norm of v cosine theta. So basically the component norm of v cosine theta, so the component of v in the direction of w. So इसमें देखें w का कोई पार्ट इन्वॉल्व नहीं हो रहा क्योंकि मैंने w की डायरेक्शन में यूनिट वेक्टर लिया सिर्फ. So similarly if I want to calculate the component of v of alpha of t in the direction of tangent vector, तो मैं tangent vector की डायरेक्शन में एक यूनिट वेक्टर लूँगा और उसका डॉट प्रोडक्ट ले लूँगा v of alpha of t से. So this will give me the component of v in the direction of tangent vector. So this part is basically given as v of alpha of t dot alpha prime over alpha prime norm. So that's what it is. Now this is a very simple fact from physics, that given a force which is responsible for some work done on the particle, then we just take the product of that component and multiply it with the distance covered by the particle, so force into distance. So in general this is equal to force dot with the displacement vector, but in this case हमने already जो component है force का in the direction of the motion of particle ये हमने calculate कर लिया है, so we don't need to take the dot product. So this is the component of the force responsible for the work done on the particle, and this is the displacement. And why this is the displacement? So हम ये assume कर लेते हैं that for very small value of time or parameter t, delta t, this is very small value, इसके लिए ये जो curve है this is approximated by this straight line. So this tangent line, इससे हम approximate कर सकते हैं curve को for a very little value of delta of t. So हमने curve को approximate कर दिया है with this tangent vector for a very small value of delta t. So basically alpha prime of t norm into delta of t. So इसके बाद हम delta of t पे condition impose कर देंगे that this varies on all of the curve and this approaches to 0, then we will get the exact expression for the work done. So अभी हम approximate कर रहे हैं, उसके बाद हम kind of limit लेंगे और limit में delta t will approach to 0, and when delta t will approach to 0, then in fact we will get the work done along this path. So उस केस में approximation नहीं रहेगी, उस केस में हमारे पास exact value आ जाएगी. So this is the force responsible for work and this is the distance. So force or the component of force multiplied by the distance, and we get the work done. Now if we simplify this expression, then alpha prime of t norm will cancel out and we get v of alpha of t dot alpha prime of t and delta t. So this is the approximated work done for a very small value of delta t. अब अगर मैं इसको sum कर दूं over the curve segment from alpha of a to alpha of b, अगर इन दोनों के दरमियान मैं इनको sum कर दूं, which is basically image of some closed interval of R1 under this map alpha. So इस point alpha of a to alpha of b के दरमियान integrate करने के लिए, या in other words इन तमाम work done को sum करने के लिए हम इंटीग्रल लेते हैं और इसमें हम delta t को approach करवा देते हैं to 0, and when delta t approaches to 0, then we are in fact getting the exact value of the work done, and we are all summing them up, and so we are integrating them. And so the work done of a particle in a force vector field can be written as a to b, v of alpha of t dot alpha prime of t dt. And this integral appears in many applications of engineering and science. So let's try to explore this, and let's see if we can write it in a simple form. Now we want to write this integral in a simple form. So for that we introduce this notation: dual of a vector field v. Now what is vector field v in this case? This is the force vector field, और इसका हम dual define करना चाह रहे हैं. So this is just a recall कि हमने dual natural frame field का define किया था, उसके बाद हमने किसी भी frame field का dual define किया था. So on the same lines we can also define dual of any vector field. So कैसे define करेंगे? So dual of a vector field is a one form. Okay, so this is the important thing. Dual of a vector field is a one form. Now what is a one form? One form is a linear function and it takes tangent vectors to real numbers. Okay, so I need to find out the image of any tangent vector to the surface, or I should get a real number. So let w of p be a tangent vector, then the image of this one form of this tangent vector is in fact w dot v of p. So basically अगर किसी भी point पे मेरे पास v of p है, so let's see, I have this surface M, and on this surface there is a vector field. At each and every point there is a vector, and WP is any tangent vector. So basically let's say this is WP, it is tangent vector to the surface at point P, and by definition of tangent vector there is a curve passing through that point and which lies on the surface, and WP is tangent to that curve at point P. So this is by definition. So WP is any tangent vector to the surface, then the image of this tangent vector under this one form is just the component of W in the direction of V of P. So basically this is V of P because corresponding to each and every point on the surface I have a vector, because it is a vector field on the surface M. So surface के हर point पे मेरे पास एक vector आएगा. Similarly V of P जो है is a vector corresponding to the point P which is on the surface M. So कोई सा भी हमारे पास tangent vector है, मैं उसका component calculate करूँगा. So basically I will take the dot product of W with V of P. So this is how I define dual of the vector field. So this is just the dot product of W with V of P, and this is a scalar. If we remember the definition of dot product, then this is a scalar, this is a real number, and that's how we define the dual of a vector field. Now let's consider this work done integral again. Can we write down this integral in terms of some one form? So basically the idea is to use this dual of the vector field idea onto this integral. So इस integral में आपको कोई vector field नजर आ रहा? Yes, we can see that V is the vector field. And what is the dual of this vector field? Dual of this vector field will take elements vectors, and this will go to W dot V of P. So by the same definition So this V is a vector field on the surface M, and the dual of V is going to be phi, which is a one form, and when calculated on a tangent vector to the surface, it will give me W dot V of P. Now if we look closely to this expression, then this is in fact phi of alpha prime of t. Now what is alpha prime of t? Alpha prime of t is basically tangent vector to the curve. So let's consider this surface M, and let's say there is a curve alpha in this surface M, and alpha of t is curve, then alpha prime of t is the velocity vector. And what is the initial point of this velocity vector? This is alpha of t. So दोबारा इस definition पे आ जाएं, that phi of WP, so in this case phi of alpha prime of t, and what is the initial point of this vector? The initial point of this vector is alpha of t, because this is the initial point of the velocity vector. So basically phi of alpha prime of t with the initial point alpha of t. So what is this expression according to this definition? This is just equal to W, the vector part, so as a matter of fact alpha prime of t dot product with V of P. So जिस point पे point है इस vector का, वहाँ पे आप V apply कर दें. So V of, and what is the initial point in this case? Alpha of t. So basically this expression, which is V of alpha of t dot alpha prime of t dt, is nothing but phi of alpha prime of t. और क्योंकि alpha prime of t, which is the velocity vector to the curve lying in the surface M, इसका जो initial point है हमेशा alpha of t होगा, क्योंकि ये tangent vector है. So the initial point is always going to be alpha of t, इसलिए हम इसको ignore कर सकते हैं. So this is understood that the initial point of this is going to be alpha of t. So it is simply phi of alpha prime of t dt and integral from a to b. So this is the work done by a force vector field on a particle moving along the curve alpha. और अभी कुछ देर पहले हमने ये देखा था what is phi of alpha prime of t dt with limits of integration a to b. This is just equal to the integral of the one form along the curve alpha inside the surface M. So that's how important this integral is. So the integration of one form along a curve on a surface M has huge applications in science and engineering, and this calculation of work done is just one example. And so the total work done by a particle becomes, the work done is equal to phi integrated along the curve alpha, and phi is the dual one form of the vector field V. So that's how we calculate the work done by a vector field. It may be force vector field, and this is the work done by a vector field on a particle moving along a curve alpha on the surface M. So one of the simple application would be कि जो planet Earth है हमारे पास, जो कि once again एक surface है, basically इसके जो अगर ऊपर वाली surface है सिर्फ वो consider करें आप, in fact it is a solid, लेकिन इसकी जो ऊपर वाली surface है वो consider करें, तो उस surface के ऊपर अगर कोई particle move कर रहा है and we want to calculate the work done, for example by the gravitational vector field on a particle moving along a curve alpha, then this is exactly this integral. So अगर आप बहुत locally कोई work done calculate करना चाह रहे हैं on the planet, then of course this is Euclidean, very locally planet Earth look like some part of R2. But in general, अगर आप planet Earth को totally consider करें, then we need to use this integral. Now the integral of a differential. Let f from m to r be a function on m, and let alpha from ab to m be a curve. So for example, this is the closed interval inside the real line, and this is the function alpha, and this is the curve. So let's say this is the starting point alpha of a, and this is the end point alpha of b, and this is the surface m. So this point is p and this point is q. Then the integral of df along alpha is equal to f of q minus f of p. So what is f? F is a zero form on the surface. So what is f? F is a zero form on the surface. Or what is the exterior derivative of this zero form? Of course, the exterior derivative of a zero form is a one form. So once again, we are integrating a one form along the curve alpha between the points P and point Q. So इन दोनों पॉइंट्स के दरमियान हम ये जो वन फॉर्म है df इसको इंटीग्रेट कर रहे हैं, and this is equal to f of q minus f of p. Now this is a very important expression, क्योंकि इसमें जो कर्व की मिडल की वैल्यूज हैं, सो फॉर एग्जांपल ये कर्व का एक एंड पॉइंट है, ये कर्व का दूसरा एंड पॉइंट है, हमने फंक्शन की वैल्यू सिर्फ और सिर्फ q और p पे कैलकुलेट की और उनको आपस में सब्ट्रैक्ट कर दिया, और फिर हमने ये कहा कि दिस इज इक्वल टू द इंटीग्रल ऑफ दिस वन फॉर्म अलोंग दिस कर्व अल्फा. लेकिन हमने जो इसकी मिडल की वैल्यू है कर्व की, उसको कंसिडर ही नहीं किया अपने आंसर में. डेफिनेटली जब आप इसको कैलकुलेट कर रहे होंगे तो आप इन मिडल की वैल्यूज को कंसिडर करेंगे, लेकिन जब आंसर आ रहा है हमारे पास तो आंसर डिपेंड ही नहीं कर रहा किसी भी मिडल वैल्यू पे. इट ओनली डिपेंड्स ऑन द इनिशियल पॉइंट एंड द फाइनल पॉइंट ऑफ दिस कर्व. सो दिस इज वेरी इंपॉर्टेंट ऑब्जर्वेशन. तो इसका मतलब है अगर मैं सेम इनिशियल पॉइंट्स और फाइनल पॉइंट्स रखूं तो मैं इस पॉइंट से इस पॉइंट तक किसी भी पाथ के जरिए आऊं. सो फॉर एग्जांपल पहले मैंने इस येलो लाइन को फॉलो किया, अब मैं इस रेड लाइन को भी अगर फॉलो करूं तो आई विल गेट द सेम आंसर. एंड सिमिलरली इफ आई फॉलो दिस ब्लू पाथ, देन once again I will get the same answer, because the answer, the integral of df along this curve alpha with initial and final points p and q depends only on p and q, and it does not depend on any intermediate points. So this is very important observation. So the integral of a differential is path independent. So अगर मैं कोई सा भी पाथ ले लूं, then the answer will be same. Of course, all of them lies on the surface M. Now let's prove this fact. Now let's start from alpha df. Now I can write it down as a to b df alpha prime of t dt, And why I can do that? Because I know that the integral of y along the curve alpha from alpha of a to alpha of b, this is nothing but phi of alpha prime of t dt from the point a to b. So we just implemented this definition, and so this is equal to a to b alpha prime of t f dt. Now we know that what is the exterior derivative of a zero form at a vector v. So the exterior derivative of a zero form is a one form, and what is a one form? It takes tangent vectors to real numbers. So basically अगर मैं किसी भी tangent vector पे अगर मैं इसको apply करूं, this is nothing but the directional derivative of this zero form or the real valued function in the direction of v. So इस केस में हमारे पास v क्या है? Alpha prime of t. So it is basically the directional derivative of f in the direction of alpha prime of t. So this is equal to a to b d by dt f of alpha of t dt. So ये हमने ऑलरेडी एक रिजल्ट किया हुआ, हमने जस्ट उसको अप्लाई किया है, एंड दिस इज एग्जैक्टली द सेम रिजल्ट दैट दिस इज इक्वल टू दिस. और ये हमने उस वक्त किया था जब हम वेलोसिटी वेक्टर्स देख रहे थे आफ्टर द डायरेक्शनल डेरिवेटिव. एंड सो दिस बिकम्स f of, so roughly speaking you can say that this d by dt and this integral cancelled out, and this becomes f of alpha of b minus f of alpha of a. Now what is alpha of b? This is q, and what is alpha of a? This is p. And the proof is very simple as compared to the consequences of this result. So once again it implies that the integral of a one form along a curve is path independent, and it depends only on the initial and final points on the curve. So और क्या consequences हो सकते हैं इसके? So let f be a real valued function on a surface M, then consider this, which is the integral of this one form. So why this is one form? So let me remind you again that this is the exterior derivative of the zero form, so it is a one form. So the integral of a one form along this curve alpha is path independent, and its value depends only on the starting and end points p and q of alpha. So in particular, if alpha is a closed curve, so for example let's say this is alpha, which is lying on some surface M. Let's say this is M, and a, let's say, is the initial point, and let's say this is equal to alpha of a, और उसके बाद let's say हमने move किया to the point B, और उसके बाद हम दोबारा point B से point A पे आ गए. So what is the initial point? Alpha of A. What is the final point? Alpha of A. So by the definition, what is this integral? So this integral is nothing but f of alpha of A, because this is the final point. Alpha of A is the final point, minus f of alpha of A, because this is also the initial point, and so this is equal to 0. So if p is equal to q, then the integral of a one form along a curve alpha is 0, and in this case alpha is closed curve. And once again, this is an important consequence. So the work done around a closed path is 0. So we have proved this very well known and very basic result of physics, that work done around a closed path is 0. So why this is work done? क्योंकि हमने अभी देखा है कि we can also write down the work done in terms of the integral of a one form along the curve alpha. और क्योंकि integral of a one form along the curve alpha can be calculated using the previous theorem, and so if initial and final points are the same, then the work done is 0. So this is just one of the examples of the important consequences of these results. Let the boundary of the curve be q minus p. So this is just a notation which we used in higher dimensions, let's say 2 dimensions, लेकिन हमने इस curve के लिए भी इस terminology को introduce किया है. So let's say this is the point q and this is the point p, then we say that p is the starting point, which is, let's say, alpha of a, and this is a, this is b, and this is the image of some curve alpha inside the surface M. So q minus p is the boundary of the curve, and q is endpoint, p is the initial point. Then the integral of df over alpha equals the integral of f over the boundary of alpha, namely f of q minus f of p. So ये result बहुत simple नज़र आ रहा होगा. इस interpretation को हम बहुत trivial भी कह सकते हैं, लेकिन this will help us to understand the higher dimensional case. So let me again say what is this statement. कोई सा भी हमारे पास फंक्शन है, 0 फॉर्म है, df मैंने कैलकुलेट किया 1 फॉर्म हो गया, और उसका अगर मैं इंटीग्रल लूँ along some curve alpha, then this is equal to the values of the function on the boundary. So boundary क्या है मेरे पास? जो end points हैं p and q. So q minus p, which tells that p is the starting point, q is the end point, और सिर्फ ये जो इंटेग्रल है ये इस बाउंड्री पे डिपेंड कर रहा है. नाउ दिस विल मेक मोर सेंस जब हम इस किस्म की स्टेटमेंट को जनरलाइज करेंगे टू सम पैच और टू सम वेरी स्मॉल पोर्शन ऑफ द सरफेस. सो उस केस में जब हम कहेंगे कि द इंटेग्रल डिपेंड्स ऑन जस्ट दीज 4 लाइन्स, then this statement will make more sense कि ये जो इंटेग्रल है ये जो इनर पार्ट है सरफेस का इस पे डिपेंड नहीं कर रहा. So we can just ignore it and it will just depend on the points which are on the boundary, or in fact these 4 curves, these 4 straight lines. So this statement will make more sense then, but at the moment this is very trivial, and this is just saying that the integral of this one form along this curve alpha depends only on the boundary, or the value of the function on the boundary points which are p and q. So let's go to the higher dimensions. So सबसे पहले हमने एक कर्व ली, अब हम एक छोटा सा पोर्शन लेते हैं. So हम इसको 2 सेगमेंट का नाम दे रहे हैं क्योंकि this is not a patch. So patch require more conditions, लेकिन हम इस 2 सेगमेंट पे सिर्फ और सिर्फ ये कंडीशन इम्पोज कर रहे हैं that it is from some portion of R2 to the surface M, and this is differentiable. Now we can notice that this R is not open, so this is not open subset of R2. So how to check the differentiability? क्योंकि differentiability जब आप चेक करते हैं you need open sets. So उसके लिए आप ये करते हैं that let's say this R is contained in some open set D. So this is open. and we say that x, which is 2 segment, is differentiable if it is differentiable from D to M, from some open set D to the surface M, and this D contains this closed interval R. So that's how we check the differentiability of this 2 segment. Lekin in general this is from some closed subset of R2 to the surface M. So that's how we define a 2 segment. उसके बाद let's see कि 2 segment और patch में क्या differences हैं. So we don't assume that a 2 segment is regular or injective. ये वो conditions हैं जो हमने assume की थी for the patch, लेकिन जो partial velocities हैं they are defined as usual. So what are the partial velocities? So partial velocities are basically, and there are lines which are parallel to v axis inside this R, and corresponding to these lines which are parallel to v, so basically on this line, on this green line, u is fixed. So let's say some value u1 is fixed, but v is a variable. So this will give me a curve on the image x of R, and all of these green lines will give me curves on this patch, and all of these curves depend on only v and not on u. Similarly, the lines which are parallel to u depends only on u, and each line have the value of v fixed. So for example, for this line the value of v is fixed and it is v1, and it will give me curves on this image x of R which depends only on u. And at some point, let's say this is the point v1 u1, at this point there is a red line passing through this point and there is a green line passing through this point. So at the image of this u1 v1, let's say this is the image of this u1 v1, in other words x of u1 v1, then at this point there is a red curve passing through the point, and so if I differentiate this curve which depends only on the u variable, I can calculate xu, which is the partial velocity at this point P, and I can calculate it because it's a curve depending on the variable u only. And similarly, passing through this point x of u1 v1, there is a green curve, and I can differentiate that curve to get the velocity which is xv, because it only depends on the vector v and u1 is fixed at that point. So these are the partial velocities, and defining these partial velocities does not require regularity or injectivity of the map. So we can define them just like we did that for the patches, but they may behave in a strange way if x is not regular. So the condition of regularity is very important geometrically, और अगर आप ये assume नहीं करेंगे, then the image surface would be very strange in general. So there will be some we can say intersections. Surface हो सकता है किसी point से फट जाए, या किसी जगह से remove हो जाए, या किसी जगह से singularity आ जाए. So these are the things, these are some of the things that can happen. So the condition of regularity, so as the word suggests, इसका अगर आप literal meaning dictionary में भी देखें, so regular means everything is regular. So we don't want anything irregular in this case. So that's why we require regularity. Now how to integrate two forms? We use the same strategy. If phi is any two form on the surface M, and we want to integrate this two form along some portion of the curve or along some segment, तो हम क्या करते हैं, बिल्कुल वैसे ही जैसे हमने कर्व के केस में उसको पुल बैक कर दिया था ऑन टू द क्लोज्ड इंटरवल. सो इस केस में भी हम ईटा जो कोई सी भी टू फॉर्म है ऑन द सरफेस M उसको पुल बैक कर देते हैं to get some two form on this two segment. So basically we want to calculate the pullback x upper star of phi. Now this is a two form and this is a two form on some portion of R2 और ये हमने पिछले lectures में देखा था that any two form on the Euclidean plane can be written as h du dv, where u and v are the coordinate functions. And what is h in this case? This h is basically the image of this form x upper star phi on this natural frame. So u1, u2. So corresponding to every point P, there will be u1 and u2, and u1 is basically unit vector in the direction of u axis and u2 is the unit vector in the direction of v axis. So let's say at point P, u1 of P is this vector and u2 of P is this vector. So this is the natural frame in R2. And what is the image of the pullback of a two form on a pair of vectors? So these are vectors because corresponding to each and every point this will give me vectors. सबसे पहले आप इन vectors का image ले लेते हैं under the tangent map. So we will get x lower star u1, x lower star u2. So these are the tangent vectors onto the surface M, and these are images of this u1 of P and u2 of P. So basically the image of this vector is going to be some vector, and this is x lower star of u1 of P. So corresponding to each and every point I will get this, and similarly corresponding to u2 of P there will be a tangent vector x lower star of u2 of P. So this is a tangent vector on the surface, this is another tangent vector on the surface, and their initial point is the same. And so I can calculate the two form. और अगर आपको याद हो what is a two form? A two form takes a pair of vectors to real numbers and it is linear in both coordinates. So this is just equal to eta of xu xv. And why this is xu xv? Because if P has coordinates u and v, then this point is basically x of uv, and this vector is then the partial velocity. क्योंकि ये जो vector है it is parallel to u, so along this vector, so we can say that this is a tangent vector to this line, and there are blue lines which depends only on u and not on v, and each and every blue line will go to a curve inside this image, and so x lower star of u1 of P is nothing but xu. And similarly this u2 of P is tangent vector to this green line, and there are green lines which depends only on v, and this will give me green curves on this patch on this portion of the surface, and so x lower star of u2 of P is nothing but xv. And so this is equal to eta of xu xv. Now we can define the integral of eta over x as, so what is eta? So eta is basically a two form on a surface M, and x is basically giving us some portion of the surface. Now how to integrate this two form on this portion of M? This is equal to the pullback of this two form on this region R, just जिसका इमेज ये पोर्शन है सरफेस का. सो इस पे पुल बैक कर लें आप x अपर स्टार ईटा और इंटीग्रेट कर लें ऑन दिस पोर्शन r विच इज इक्वल टू, ये हमने अभी देखा है दैट एवरी टू फॉर्म ऑन दिस पोर्शन r ऑफ r2 कैन बी रिटन एज h of du dv into eta of x u xv. So we can write down eta of x u xv du dv, and u varies from c to d and v varies from a to b. So du corresponds to this integral and dv corresponds to this integral, and these are basically the initial and final points of this portion. So for example, this is u axis, this is v axis, and this is c, this is d, this is a, and this is b. So a, b, c, d define this square or rectangle in general inside R2. So these are the limit. Now boundary of a two segment. Now let R, which is equal to AB cross CD closed interval, is some subset of R2, and X from R to M be a two segment in M, and let alpha, beta, gamma, delta be the curved segments such that alpha of u is equal to xuc. So this is alpha, and on this alpha c is fixed, the second coordinate is fixed, but it depends on the variable u. So this is equal to the second coordinate fixed, the first variable varies from a to b, and so alpha of u is equal to x of uc. Similarly beta, beta के लिए जो first coordinate है वो fixed है, which is b, but the second variable is a variable, so this is equal to x of b v. Similarly gamma is equal to x of ud, and delta is equal to x of ab. So these are the boundary lines of this segment. Now we can write down the boundary as alpha plus beta minus delta minus gamma. So basically अगर आप सिर्फ और सिर्फ at the moment, ये चीज़ हम बाद में देखेंगे कि ये एरोज हमने कैसे डिसाइड किए हैं, लेकिन at the moment आप सिर्फ ये देख सकते हैं that अगर आप एरो की डायरेक्शन में जा रहे हैं, so this is the direction of increasing u, this is the direction of increasing u. So आप इस डायरेक्शन में जा रहे हैं, उसके बाद हम एरो की डायरेक्शन में जा रहे हैं, लेकिन अगर हम इस डायरेक्शन में मूव करेंगे then this parameterization has opposite value to that of the arrow which is on this boundary, so we will get a negative sign, and similarly for delta. और ये arrows जो हैं वो कहाँ से आ रहे हैं? We know that there is an orientation of a curve, और वो orientation कहाँ से आती है? From the ordering of the real numbers. So let's say ये मेरे पास 1 है, ये 2 है, ये मेरे पास 0 है, -1 है. So let's say this is 2 and this is 3. Then there is this point alpha of 0, alpha of 1, alpha of 2, alpha of -1. So we can see that the image of -1, 0, 1, 2 comes in an ordering. So this defines an ordering of the curve. So there is an ordering in the curve, or there is an arrow going along the curve. So this is the same arrow जो कि हमने यहाँ यूज़ किया है, because for the increasing value of u you will get this direction, and for the increasing value of v you will get this direction, and for the increasing value of once again u in case of gamma you will get this direction, and similarly for the increasing value of delta you will get this direction. So these arrows are basically decided from the orientation of the curve, and this boundary is basically decided कि आप यहाँ से start लें और यहाँ पे ख़त्म हो जाए, और जब आप इस तरीके से follow करेंगे then there will be minus sign, क्योंकि along delta और gamma आप opposite side पे move कर रहे हैं. So that's how we define the boundary. And if phi is a one form on the surface M, then how to take integral of this phi along the boundary. So we define it as the integral along alpha, because we know how to take integral of a one form along a curve, and this alpha is just a curve. ये जब आज के लेक्चर में हमने डिस्कस किया था कि how to take integral of a one form along a curve alpha. So similarly, phi along beta minus phi along gamma minus phi along delta. So that's how we define one form along the boundary of a two segment. So what we have learned so far, आज के लेक्चर में हमने बहुत important एक चीज़ की है, which is how to integrate a one form along any curve inside the surface M. So basically now we know how to integrate along a curve inside any arbitrary surface, and then we saw how to do that for two forms, और उसके बाद हमने ये देखा with how to calculate the integral over a boundary. नेक्स्ट लेक्चर में हम इसी डिस्कशन को आगे कंटिन्यू करेंगे, और जो थ्योरम हमने किया था जिसमें हमने प्रूव किया था that the line integral of a one form along a curve depends only on the initial and final points and it does not depend on the intermediate curve. इसी का जो हायर डायमेंशनल एनालॉग है फॉर इंटीग्रल ऑफ टू फॉर्म्स, ये हम कर रहे होंगे नेक्स्ट लेक्चर में. सो इन द नेक्स्ट lecture we will be discussing Stokes theorem. This is the end of the lecture. Thank you very much and Allah Hafiz.